I will go ahead and start today, inshallah, chapter 7, which is the last class, the last chapter in this course. This chapter is a little bit extended. We may take, inshallah, kind of 3 weeks in this chapter to end up with this course. This chapter, ya shabab, is entropy, deals with the entropy, which is application of the second law of thermodynamics. Mainly, this chapter will be talking about how to calculate the entropy generation within a system. Entropy generation is a measure of the losses within the system, is a measure of the irreversibilities within the system. So if you have a system and you are going to calculate the entropy generation, that will reflect actually the losses within this system. Inshallah, we'll learn this in this chapter, but actually nothing new. Just we'll be considering the same problem in closed system like what we have done in chapter 4, and also the open system like what we have done in chapter 5. But what will be added actually in this case, I will give you a problem, and the last requirement, I will ask you to calculate the entropy generation from this system, just to give us indication about the losses within this system. So it will be the same problem like in chapter 4 and chapter 5. So the objective, inshallah, of this chapter will be going to apply the second law of thermodynamics for a process and relate this second law of thermodynamics to the property which is called the entropy. How we can relate or express the second law of thermodynamics in terms of the entropy through what is called actually the concept of entropy increase. For any process, shabab, any process should be an actual or irreversible process. We should have some losses within the system. And in this case, the value of the entropy generation within the system should always be a positive value for any process. So for any process, the value of the entropy generated within the system should always be a positive value, because actually any actual process should be associated actually with some losses, and this losses can be directly actually translated in the form of the entropy generation. So entropy generation is always a positive value, and this is a kind of a third expression for the second law of thermodynamics. We have the Kelvin-Planck statement applied for heat engine, and we have the Clausius statement applied for the refrigeration cycle. And also we can express the second law of thermodynamics in terms of the entropy generation, and we can say the value of the entropy generation for any process should always be a positive value. So inshallah, in this chapter, we'll be able, inshallah, to calculate the entropy generation. First of all, we'll start to calculate the entropy change for any process, how we can calculate the change of entropy, considering actually different working fluid, considering pure substance, like in case when we have steam or refrigerant, how we can calculate the change of entropy of any process when the working fluid is steam or refrigerant. Also, we'll learn how to calculate the change of entropy in case of incompressible substance, in case of solid or liquid, how we can calculate delta S, and also in case of ideal gases, how we can calculate the value of the entropy change delta S. This value of delta S will be using, inshallah, to calculate the value of the entropy generated within the system. Also, we'll examine the special process, idealized process, which is called the isentropic process. Isentropic process, shabab, is a reversible process. We don't have any kind of losses, and the process is also adiabatic. So adiabatic and frictionless, we call it actually as isentropic process. So the isentropic process is a kind of a reversible process in which you don't have any kind of losses. So inshallah, we'll generate what we call actually the isentropic property relation. If we have an ideal gas undergo an isentropic process, how we can relate the properties before and after this process, how we can relate the pressure, how we can relate the temperature and the change also of volume. So inshallah, we'll develop what is called actually the isentropic relations for the case of gases, and also we'll derive what is called actually the reversible steady flow work. We said if we have a reversible process, that means actually we don't have any kind of losses, and that means the process actually is reversible, and the work out of this system, we call it the maximum or the reversible work. But how we can calculate this maximum work for a given process? Inshallah, we'll learn how to calculate this, and we'll apply this actually for the case of compressor and turbine, how to calculate the maximum work input to the compressor and the maximum work out in case of turbine. Then we will calculate the isentropic efficiency. Isentropic efficiency is the ratio between the actual work divided by the isentropic or the reversible work in this case. And then inshallah we'll end up in this chapter, we'll learn how to calculate, how to apply the entropy balance through which actually we can calculate the entropy generated within a system. As I told you, entropy generation is always a positive value. Inshallah we'll prove it today. And the entropy generation is a direct measure of the losses within the system, because all of the losses within the system will be translated on the working fluid in terms actually of entropy increase, or what we call actually entropy generation in this case. So entropy يا شباب is not a conservative property. We don't have conservation of entropy. We have just entropy balance, because entropy is not conservative. Entropy can be generated within the system due to the losses within the system. And that's why we said entropy is not a conservative property in this case. But first of all, let's look at the process. Some changes in my office. So inshallah I will try to go live with you today. I didn't record the video yesterday. So hopefully today will be maybe better than the other classes. So let's try and see. Actually I don't have more space to stay. So is the board clear يا شباب?
Yes. Yes.
It's okay. But let's start today with the Clausius inequality. Clausius inequality, which state actually any cycle, the integration over the cycle, delta Q over T should be less than or equal to 0. First of all, I just want to define the property which is called the entropy in this case. Clausius inequality state actually integration over a cycle, this symbol integration over a cycle, integration of delta Q over T should be less than or equal to 0. But how we can prove this relation? If we have a heat engine, we have the thermal efficiency of the heat engine is equal to 1 minus Q low divided by Q high. This is the expression of the thermal efficiency. But we have expressed based on the Carnot cycle that eta thermal reversible, we can replace actually the heat transfer ratio by the temperature. It should equal to 1 minus T low divided by T high. But we said eta thermal reversible should be greater than actually eta thermal, because in this case actually the system is working on Carnot cycle and we don't have any kind of losses. And that means actually this term should be greater than actually this term in this case. So for a cycle we should have Q low over Q high. This ratio should be less than or equal to 1 minus Q low over Q high is less than or equal to 1 minus T low over T high. When they should be equal يا شباب? When the system is working on a Carnot cycle. In this case, Q low over Q high should be the same as T low over T high. But in this case, to have this term less than or equal to actually this term, that means Q low over Q high should be greater than or equal to T low divided by T high. Is that correct يا شباب?
Yes, yes.
To have this term 1 minus T low over T high greater than or equal to 1 minus Q low over Q high. That means actually Q low over Q high should be greater than or equal to T low over T high. Or based on this relation, we can just say Q low over T low should be actually greater than or equal to Q high divided by T high. So Q low over T low should be greater than or equal to actually Q high divided by T high in this case. Okay. Or we can say Q low divided by T low. Let's take this term to the other side. It will be negative sign. So minus Q high divided by T high. That should equal to greater than or equal to 0. This Q high شباب is the heat added to the heat engine. That should be a positive value. But we have negative sign here. But this Q low is the heat rejected in the condenser, and it should have what? It should have a negative sign. So that means this term is also negative. But if I multiply the whole equation by negative sign, so this sign will be what? Will be converted in this case. So in this case, we can just say Q low over T low plus Q high over T high. That should be less than or equal to 0. So instead of greater than, it will be less than when I multiply actually the whole equation by a negative sign. Or we can say the summation of Q divided by T over the cycle should be less than or equal to 0. Or we can just express it actually in another form. We can say integration over a cycle instead of the summation. Delta Q, integration of delta Q over T this term actually should be less than or equal to 0. And this is شباب what we call the Clausius inequality. Based on the second law analysis, based on the Carnot cycle analysis, for any system working on a cycle, integration over this cycle, delta Q over T should be less than or equal to 0. طيب when this term يا شباب should equal to 0? Integration over the cycle delta Q over T. When this term should equal to 0?
When it's working on a current cycle.
Exactly. When we have Q low over Q high is equal to T low over T high. Working on the Carnot cycle, reversible cycle, that means this term should equal to 0. طيب, let's write down this. So let's express it here. When a system working on a Carnot cycle, in this case, we should have integration over the cycle delta Q over T. This term should equal to 0 in this case. Okay. So for a system working for a reversible cycle, we should have integration over the cycle. This term delta Q over T for this reversible cycle should equal to 0. But by definition, if we have any system working on a cycle, let's say on the PV diagram, starting from a point, go do different processes and get back to the same point. So the final point is the same as the initial point. So based on a system working on a cycle, integration over a cycle of any property, like let's say the volume delta V, integration over the cycle delta V should equal to what? Should equal to 0, because it should equal to integration of delta V, which is V, from the initial state up to the final state. The initial state is the same as the final state. That means that should equal to V final minus V initial, and this should equal to 0. And this can be applied for any property. This can be generalized for any property. Integration over a cycle for any property should equal to what? Should equal to 0. But we have here another expression. Integration over a cycle delta Q over T for a reversible process is equal to 0. That means this term delta represent what? Represent our property as well, because we have integration over a cycle for any property that should equal to 0. But we have this integration for a reversible cycle. Integration of delta Q over T is equal to 0. That means this term delta Q over T is representing a property. And this is actually what Clausius said. Clausius was the first one to define the property entropy, and he defined the property entropy delta S as equal to actually delta Q over T by the condition that this cycle actually this process is a reversible process. Or we can do the integration of this cycle to get actually the total change of entropy S delta S, which is S2 minus S1 for any process from 1 to 2. Delta S will equal to delta Q integration from 1 to 2, the term delta Q over T. But the condition is what, شباب? The process should be what? Should be reversible in this case. And this property actually is delta Q over T is calculated, the heat transfer in kilojoule and temperature is measured in Kelvin. So this property, which is called the entropy, is defined as integration of delta Q over T, and it is actually calculated in kilojoule per Kelvin in this case. But if we have an isothermal process, that means the temperature is what? Temperature is constant. So this term is constant. So can we take it outside the integration? Can we?
Yes.
Yes, we can take it. Then it will be integration of delta Q, it will be Q. And in this case, for an isothermal process, delta S, S2 minus S1 should equal to actually the heat transfer Q divided by, during this process, divided by the temperature in this case. And this is an example here. You can see here, he said, and in this example, we have a piston cylinder device that contains liquid, a mixture actually of liquid plus vapor, and the saturation in the saturation zone of water at temperature equal to 300 Kelvin. So we have a saturated liquid vapor mixture of water at 300 Kelvin contained actually in this piston cylinder device. He said we have added heat to this gas in the piston cylinder device. This heat actually is equal to 750 kilojoule of heat is transported to this water. And they said as a result, part of the liquid has been converted to vapor. So still part of the liquid has been converted to vapor, but still we have the same saturated mixture. So do we have temperature change, يا شباب? While the phase change?
No.
No, there is
So
no.
in this case, the temperature will be fixed at 300 Kelvin, and we have heat is added is equal to 750. So in this case, the change of entropy, which is required to calculate in this case, the change of entropy for the system during this process should equal to Q divided by T, which is 750 divided by the temperature, which is 300. Then we can calculate delta S in this case. So in case of isothermal process, while the phase change process, in this case, delta S is equal to Q divided by T. Okay. Type entropy, شباب, is defined, as we said, in terms actually of kilojoule per Kelvin. It is the amount of heat required to raise the temperature of a working fluid by 1 degree C. But actually, شباب, this heat added cannot be converted to work. So this heat, we cannot convert it actually to work. Why? Because this heat actually is utilized actually by the molecules of the system, and it is dissipated in the form of kinetic energy of the molecules in this case. And if you ask anybody actually, what does the property entropy represent? He will just tell you directly, this is a representation of the randomness motion of the molecules within the system. Why it is a measure of the randomness motion of the molecules? Because actually it is defined as the amount of heat required to raise the temperature of this molecule of this system by 1 degree C, but this heat actually is not available to work because it is dissipated in the random motion of the molecule. You can see here we have molecules. Some molecules are moving in this direction, the others are moving actually in the reverse direction. So we cannot convert actually this heat actually into work. So entropy is a measure of randomness of the molecules, but actually entropy is also energy. Entropy is an energy, but this energy cannot be converted to work because it is dissipated in the kinetic motion of the molecules. Type in case of gases, gases who don't have molecular order, or actually the intermolecular force is very low in case of gases. So in this case, the movement of the molecules will have actually more freedom when we compare it actually to liquid, restricted motion actually of the molecules. And in case of solid, we don't have actually any kind of motion of the molecule, just as they are vibrating. So in case if we do have solid substance, liquid substance, and the gaseous form of the same substance at the same temperature, the entropy of the gases in this case should be greater than actually the entropy of the liquid, and also should be greater than the entropy of the solid, because actually the gases who don't have intermolecular forces. So in this case, actually, the gases will have more freedom, and more freedom, that means actually more freedom of movement. So more movement means actually more dissipation of the heat in the form of the kinetic motion of the molecule, and that means actually the entropy will be raised for the gases in this case at the same temperature when we compare it to the liquid and also to the solid phase. But what is the reference point at which we consider the entropy is equal to 0? Based on the third law of thermodynamics, we assign a value of entropy equal to 0 when the absolute temperature is equal to actually 0 Kelvin. And this is actually the third law of thermodynamics. Third law of thermodynamics states actually that the temperature, the entropy should be equal to 0 when the temperature is equal to 0. Okay. Boltzmann also have developed a relation actually how to calculate the entropy for a given gas at a given condition. This entropy of this gas, not gas actually, for any substance, is equal to some constant K multiplied by ln B. K is a Boltzmann constant, which equal to actually this value, 1.38 10 to the power minus 23 joule per Kelvin, multiplied by ln B. B is the probability of a molecule to be existing at a given point, at a given state, at a given time. So it's a kind actually a very tedious process to calculate actually the entropy of a substance using the Boltzmann relation. Because in this case we have to use the probability function to calculate the probability actually of a given molecule to be existing at a given location at a given time. Okay, so inshallah in this chapter we'll learn how to calculate delta S for the different substance but actually away from the Stephen Boltzmann relation. Just this relation is just for your knowledge. Okay, is that clear يا شباب how we define the entropy?
Yes.
So entropy يا شباب, if you ask anybody, he will just tell you this is a measure of randomness motion of the molecules. But actually entropy is actually the heat delta Q over T. The heat actually required to raise the temperature by 1 Kelvin, but actually this heat we cannot convert it to work because actually it is used actually in the random kinetic motion of the molecules. And random motion of the molecules, it is not actually organized in form of heat, then we cannot convert it into work. And that's why شباب, the entropy generated within the system is a measure of the losses within the system. Because as actually the heat dissipated like the heat due to friction. Where it is going actually the heat due to friction. If we have a system with friction, let's say we have a flow inside a tube or something and we have friction losses within this tube. So the friction losses will appear in terms of what? Of temperature rise of the molecules. The heat will be transferred to the molecules. But actually the molecules will be dissipating this heat in the kinetic motion. So we cannot convert the friction losses in terms of heat transfer into work. Otherwise, actually, we don't have we cannot have any losses within the system. If the heat lost will be converted, actually the losses within the system, like the friction losses, will be converted to heat, then we can convert this heat into work, so we don't have any kind of losses. But actually, this heat is not available to be converted to work. Just it is dissipated in the kinetic motion of the molecules. And that's why, شباب, when I calculate the entropy generation within a system, entropy generation is a direct measure actually of the losses within this system. Because at the end, the losses within the system will be actually dissipated in the kinetic motion of the molecules. Okay? Let's look here and let's consider a system undergo a cycle. This cycle is just of two processes. One process actually is a reversible process, and we close this cycle with another process, which is an irreversible process in this case. And let's see how we can calculate delta S and how this term actually entropy generation will appear with us. So let's consider this cycle, and let's say on the TV diagram or the BV diagram. This cycle actually consists of two processes, process from 1 to 2, which is actually irreversible process, and we close this cycle with another process from 2 to 1, which is actually a reversible process in this case. Okay. So based on Clausius inequality, we said integration over the cycle, delta Q over T, that term actually should be less than or equal to 0. We have done this is actually the Clausius inequality. In this cycle, we have two processes, from 1 to 2 irreversible, from 2 to 1 we close this cycle with a reversible process. Then it is equal to integration for the process from 1 to 2, delta Q over T for the irreversible process, plus integration from 2 to 1, delta Q over T for the reversible process. This is actually the integration over the cycle, the two processes, that should be actually less than or equal to 0. But by definition, we said delta S is equal to delta Q over T by the condition that this process is reversible. This is how we define the entropy. Delta S is equal to delta Q over T by the condition that actually this process is reversible. So that means this term for the reversible process from 2 to 1, this term actually is equal to delta S, integration of delta S, which should equal to S1 minus S2. So this term will equal to S1 minus S2. Right, let's take this S1 minus S2 to the other side. It will be S2 minus S1 of delta S, which is S2 minus S1. That should be actually greater than or equal to integration for the process from 1 to 2, delta Q over T for the irreversible process. So شباب, delta S for the irreversible process, delta S is greater than or equal to delta Q over T if the process is irreversible. And by definition for the entropy, delta S is equal to delta Q over T for the process when the process is what? Is reversible. So again, if the process is reversible, delta S will equal to delta Q over T. But if it is irreversible, delta S in this case will be greater than delta Q over T. Greater than delta Q over T because of what? because of the losses within the system, because of the irreversibilities in this case. Some entropy will be generated within the system. And in this case, for irreversible process, delta S will equal to integration, let's say from 1 to 2, the term delta Q over T for the irreversible process plus what? Plus the entropy generated within this system. So in case of irreversible process, delta S is greater than delta Q over T, or it is equal to integration of delta Q over T for the irreversible process plus actually the entropy generated within the system due to the losses within the system, which at the end converts actually in terms of kinetic motion of the molecules, which appears actually in terms of actually entropy generation in this case. But in case when this process actually is reversible, delta S will only equal to the heat transfer to the system divided by T, if the process is reversible. But due to irreversibilities, delta S for the irreversible process will equal to integration of delta Q over T plus the entropy generated from this system. Okay, Shabab? Is that clear, Shabab?
Doctor, what's the difference between delta S and S generated?
So, sorry?
What's the difference between delta S and S generated?
Delta S actually is the difference in entropy. Delta S is equal to what? Let's say we have a system here, and we have added heat to this system. Let's say the temperature of this system is constant, to make it simple. So in this case, delta S will equal to what? The heat added divided by temperature, which is this term, integration of delta Q over T. T is constant, so it will equal to Q over T. But this heat added, we can just divide by the temperature, we can get this term. But what is else actually? If this system, let's say we have some friction losses. So in this case, this friction losses will be converted to internal heat within the system. And this heat, actually internal heat, will be used in the kinetic motion of the molecules. Due to this kinetic motion of the molecule, in this case, some entropy will be generated within this system. It will be formed within the additional entropy will be formed within this system. So the total delta S will equal to Q over T, the heat transfer outside from the system to the system divided by the temperature, plus the part of the entropy generated within the system due to the losses within the system. So delta S will equal to the part of the entropy generated within the system due to the losses within the system, plus actually the part added externally due to the heat transfer. So the mechanism of increasing or decreasing the entropy is through the heat transfer. It is equal to integration of delta Q over T. But actually for any actual process or irreversible process, we should have, due to the losses, some entropy is generated within the system. So the total change of entropy of this system will equal to the term Q over T plus actually the term generated due to the losses within this system. Is that clear, Shabab?
Yes.
In case of reversible process, Shabab, if we have the process is reversible, so we don't have any kind of losses. That means the entropy generation should equal to what? Should equal to 0 in this case. Okay? If we have an adiabatic system, for adiabatic system, adiabatic means the heat transfer, the external heat transfer is equal to 0. So for adiabatic system, this term will be equal to 0. So for adiabatic system, so in this case actually we have the heat transfer is equal to 0. So we said in this case delta S is greater than actually delta Q over T. If this Q is equal to 0, we have adiabatic. That means delta S should be what? Greater than or equal to 0 in case of an adiabatic system. So if the system is adiabatic, this term delta S for an irreversible process should be greater than or equal to this integration, as the heat transfer is equal to 0. So delta S will be greater than or equal to 0. This term here, we said delta S is equal to delta Q over T plus entropy generation. So in this case, delta S, delta Q over T, the system is adiabatic. So this term is 0. So delta S will equal to what? The entropy generated within this system. So in case if we have an adiabatic system, we don't have external, so this term will just disappear. Then we have entropy delta S will equal to the entropy generated within this system due to the losses. Okay? And for any case, actually, for the adiabatic system, delta S should be what? A positive value in this case. Type delta S is equal to entropy generation. That means this entropy generation should always be greater than or equal to 0. Or we can say actually this is always a positive value. Because actually for any process, it should be an actual process, and any actual process we should have some kind of losses, and this losses will be converted, will be actually consumed in the kinetic motion of the molecules, then some entropy will be generated in this case. So in any problem, shabab, if you have calculated the entropy generation, we will learn how to calculate it. This value should always be a positive value. We cannot have entropy generation within the system a negative value. It is always a positive value in this case. But when this entropy generation can equal to 0, it is equal to 0 when we have a reversible process. In case of a reversible process, we don't have any kind of losses within the system, so the entropy generation in this case will equal to 0. Otherwise, for the irreversible or any actual process, it should be greater than 0. But can it be less than 0? No. For any actual process, we should have some entropy is generated within the system. And this is, shabab, what we call actually the concept of entropy increase. So for any process, it should proceed in the direction for the increase actually of the entropy generation. So entropy generation should always be a positive value for any system undergo any process. Entropy generation should be actually a positive value. It can equal to 0 when we don't have any kind of losses within the system. Entropy generation will equal to 0. But it is always a greater than 0 positive value in case of irreversible or actual system. But it is impossible actually to have a process in which we can have actually the entropy generation is a negative value. Okay? Type the change of entropy of the system, shabab, for any system is equal to the total change of delta S is equal to the change of entropy of the system plus the change of entropy of its surrounding. So delta S total is equal to delta S of the system plus delta S of the surrounding. So delta S total of the system, delta S of the system plus delta S actually of its surrounding. So the total change of entropy is equal to the change of entropy of the system itself plus actually the change of entropy of the surrounding medium in this case. But we have here, shabab, this is what we said. This is some of the remarks about the entropy, the concept of entropy. We said entropy, any process should proceed in the direction in which actually the entropy generation should always be a positive value in the direction of the increase of the entropy. We said based on the second law of thermodynamics, any process should proceed in the direction of from the high energy potential to the low energy potential. And also, based on the second law analysis, we have started this relation based on the Clausius inequality here. We started from the second law analysis, eta thermal reversible, and we have approached it actually here based up until we reach actually this point here, that the entropy generation should always be a positive value for any process. So based on the second law analysis, we can say actually any process has a direction from high energy quality to low energy quality, and also in the same direction of the increase of the entropy generation. Entropy generation, any process should proceed in the direction of the increase of the entropy generation for any process. Entropy also, shabab, is non-conservative property. We cannot say the conservation of entropy like what we said, the conservation of mass or conservation of energy. We said mass and energy cannot be created or destroyed. That's why we have the conservation of mass and the conservation of the energy in terms of the first law of thermodynamics. But as we can see here, entropy is not actually a conservative property because actually it can be generated within the system due to the losses. So the losses within the system just can be converted into kinetic motion of the molecules, and this results actually in entropy generation within this system. So as entropy can be generated, so it is not conservative. In this case, it can be destructed and it can be generated in this case. And that's why we have what we call actually the entropy balance. We don't have entropy conservation or conservation of entropy. We have just entropy balance in this case. Okay, شباب. And this entropy generation, as we said, any losses within the system will be converted in terms of entropy generation. So that means entropy generation is a measure actually of irreversibilities or losses within the system. So if I want to calculate the irreversibilities or losses within the system, then I can calculate just the entropy generated within this system. Okay. طيب, here is an example, شباب. Here we said we have a heat source is existing actually at temperature equal to 800 Kelvin. This heat source actually transfer amount of heat equal to 2000 kilojoule from a high temperature source to a low temperature sink existing at two different temperatures. The low temperature sink for the case A is existing at temperature equal to 500 Kelvin. And for case B, the low temperature sink is existing at temperature is equal to 750. But for both systems, just heat is transferred from the high temperature source to the low temperature sink without external heat transfer. So the system in this case is externally adiabatic in this case. And he asked us to calculate which of the two systems is more irreversible. Which of the two systems has more losses. So if I need to calculate which of the system has more losses, then in this case I have to calculate the entropy generation for each case. The first case, we have 2000 kilojoule of heat is transferred from temperature, high temperature equal to 800 to low temperature equal to 500. In case B, the same amount of heat is transferred, but from high temperature 800 to low temperature equal to 750. So which of them is more irreversible? So in this case, we have to calculate the entropy generation. So the entropy generation for an adiabatic system is equal to delta S. And delta S is equal to delta S of the system plus the surrounding. In this case, we have delta S for the source of heat, plus delta S actually for the sink of heat, at which actually the heat will be transferred in this case. Type heat here is rejected from the high temperature source at fixed temperature. So heat is constant in this case. So delta S should equal to directly the heat transfer divided by T. And it is absorbed by the sink at also fixed temperature. So in this case, delta S will equal to Q over T. So delta S will equal to delta S for the source, which is Q high divided by T high, plus delta S of the sink, which is Q low divided by T low, as heat is rejected or absorbed at fixed temperature in this case. But let's consider case A. For case A, T high is equal to 800 and T low is equal to 500. And the heat transfer is equal to 2000 kilojoule. So that should equal to Q high. This Q high is the heat rejected from the source and it is absorbed by the sink. Heat rejected from the source, then in this case we have to add negative sign. So it will be equal to minus 2000 divided by T high, which is 800. Plus Q low is the same amount of heat 2000 absorbed, so it is added to the sink, divided by the T low, which is equal to 500 in this case. Then we can calculate in this case delta S, which is equal to the entropy generation within the system. If you calculate this value, it will equal to 1.5 kilojoule per Kelvin in this case. But let's consider case B. In the case B, actually we have T high is equal to 800 and T low is equal to 750 for the same amount of heat. So in this case, the entropy generation will equal to Q high also divided by T high plus Q low divided by T low. Q high, the heat rejected from the high temperature source, so we have to add negative sign, divided by T high, which is 800, plus Q low, the same amount of heat 2000 absorbed by the sink. The sink in this case is existing at temperature equal to 750. So if you calculate this, you will find the entropy generated within this system is equal to 0.2 kilojoule per Kelvin. Compare those two values, 0.2 and 1.5. So which one is greater? So case A, we have entropy generated is greater than actually the entropy generated in case B. That means actually the system A has much losses, actually energy destruction or energy losses as compared actually to the system B. So when I need to calculate the losses or give indication or have an indication about the losses within the system, like the friction losses or any kind of irreversibilities within the system, friction losses, heat transfer losses, any kind of losses, it will appear in the term of the entropy generation. In this case, I have to calculate the entropy generated within the system, and in this case, the entropy generation will give us indication about the losses within the system. If we have two systems, one of them actually has greater entropy generation, that means this system has actually higher energy losses in this case. Is that clear, Shabab?
Yes. So more reversible is 0.2.
Sorry?
More irreversible.
Yes, more, so system A should be more irreversible than system B, or it should have actually more losses, internal losses, when we compare it actually to system B. Just Shabab, I'm configuring you out the expression of the entropy, how we initially define the term of the entropy. Then I have defined with you how to calculate that we have a term which is called the entropy generation. That means entropy is not a conservative property. It can be generated within the system and it can be destructed as well. So in this case, we cannot have concept of conservation of entropy. So we have the entropy generation, which is the entropy created within the system due to the kinetic motion of the molecule, due to the irreversibilities within the system. Because all of the irreversibilities will be converted into heat. This heat will be taken by the molecules and it will be dissipated in the kinetic motion of the molecule. We cannot convert this heat into work. And that's why when you calculate the entropy generated within the system, this is a direct reflection to the losses within this system. Okay? Because any losses, it just appear in the system in terms actually of entropy generation. So this is something, and this example is also an indicative one because we assume the temperature is fixed, and just we say delta S will equal to Q over T. So inshallah, while proceeding with this chapter, inshallah, we'll learn how to calculate delta S for any working fluid. We'll have some relation, and then using delta S, we entropy generation for any system, either closed system, open system, any system we can calculate the entropy generation. Okay, so just today's class is just introduction to the entropy generation, and then inshallah from the next time I will start inshallah show you how we can calculate delta S if the working fluid, let's say, is steam or refrigerant, and if the working fluid is gas, how we calculate delta S, and also if the working fluid is incompressible substance, how to calculate delta S. Like what we have learned in chapter 4, how to calculate delta H for any working fluid. Here in this case, we will learn how to calculate delta S. Then by the end of this chapter, we'll have the entropy balance. Then we can calculate the entropy generation within the system. So this is our target, Shabab, in this chapter, is to calculate the entropy generation within this system, which give me indication about the losses within this system. Okay, and this is a very important parameter in the analysis actually of any system. To give indication about the losses, we have to calculate the entropy generation. So if you are designing a system, in this case, you have to design the system for minimum entropy generation within this system.